Okay, so we've solved exponential equations. Now it's time to solve some logarithmic equations. Remember, anytime you see natural log, what's the first thing you should be thinking about? E. Good. And anytime you see E, you're thinking about natural log because they cancel each other out. The kicker to these canceling each other out is they have to be touching. So on this particular problem, this 7 is there, so I have to get rid of that 7 first. So I'm going to divide both sides by 7, and I'm left with the natural log of x is equal to 4. Now, when you introduce the exponential, it's taking it to that exponent. So this is e to the natural log of x because it's an exponential is equal to e to the 4th power. That's what we're looking at. Now you have that e and that exponential, so then the natural log and the e cancel out, and now I'm just left with x on the left is equal to e to the 4th. On these particular problems, they have you just leave it in terms of e. If you have to round it to a decimal place, then just plug that into your calculator. Remember, the E button is the second key to the natural log, so you can usually find it that way. Good, let's try another one. For this one, I actually have a log with a base. Anytime you have natural log, you think E. Anytime you have a log with a base, you think an exponential with the base. You're always converting to an exponential because those are what are easier to solve. So you always make that conversion. It just depends, if you have an E, a natural log in E, or if you have this with a base. Since I have the base, I'm going to take this 2 and bring it around town. So I end up with x cubed minus 19 is equal to 2 to the 3rd power. So your base is your base, always. So you have this base to the exponent of 3 equals x cubed minus 19. So now we just clean it up and solve it. So I have x cubed minus 19 equals 8. Add 19 to both sides because you want to isolate that variable. So x cubed is now equal to 27. If I have something that is cubed, you take the cube root to get rid of it. Now, because this is an odd root, there's no need for the plus or minus. If it were an even root, like something squared or to the 4th, then you'd have to put the plus or minus in. But because this is an odd root, it's just straight up x. And then the cube root of 27 is 3. And that's it. So if you start with a logarithm, convert it to an exponential, and that's how you solve. Awesome. Let's do another one. Ooh, this one's super exciting. Look what we get to do here. Now, check out what's happening on this one. Log over here, log over here, log over here. So we got lots of logs going down. You treat this the same way like what we did with the exponentials where we get the like bases. But look what other exciting stuff we get to do. See the fact that I've got 2 logs on the left? I'm going to put those together. What is this minus sign? Logarithmic properties, when I'm subtracting, what are you doing? Yeah, divide those little boogers. So I actually have log of x plus 6 divided by an x plus 2 is equal to log of x. Now, if you have a log on the left and a log on the right, the same concept applies. This is an equation. So if this is an equation, if the 2 sides are equal and they both have a log, that means that the insides are also equal. The same concept as an exponential. When you get those like bases, you drop those bases off and set the exponents equal. Same thing. If you get the exact same log on both sides, you can drop those off and just set the insides equal. So x plus 6 divided by x plus 2 equals x. Now, we have only x's. And anytime you have a rational expression, in order to get rid of what's in the denominator, you multiply both sides by that value. So multiply both sides by x plus 2 to get rid of it. I now have x plus 6 is equal to an x squared plus 2x. Woohoo! Anytime you see this squared, then you know set it equal to 0, because you're either going to have quadratic formula or you can factor. Cool. Now I have 0 is equal to an x squared plus x minus 6. Woohoo! The beauty of this problem is it's factorable. Remember, you always want to keep your lead coefficient positive, so keep that positive. And then we get to factor x and an x. A minus in the back tells me my signs are different. And what multiplies to give you 6 and adds to give you a positive 1. Yep, positive 3 and negative 2. Then we set each one of those equal to 0. So x plus 3 equals 0 and x minus 2 equals 0. So x here is a negative 3 and x is a positive 2. Now, way back when we were looking at the graphs of those logarithms, let's think back to that here just a second. So my logarithmic graph looks like this, kind of. So it goes closer and closer and closer to 0. But does it ever become negative? Is there part of my logarithmic graph over here on the negative side? No, I have a vertical asymptote at the y-axis, which tells me my x values cannot be negative. If my x values cannot be negative, then this x minus x equals negative 3 is not a valid solution. The only solution you have for this problem is 2. Because if I go to plug it back in, this log of negative 3, plug that in your calculator and see what you get. Error, right? Because you can't have the log of a negative number. It just can't happen, because if you look at your graph, you can see it's not part of my graph. So if you have an answer for your logarithm that's negative, knock that bad boy out. The only thing you have is the x equals 2. Cool, let's do some more. Cool, check this one out. So I don't have multiple logarithms. So remember, anytime you have a log, if you don't have it on both sides where you can get the like basis kind of deal, then you change it to an exponential. So let's do it. So if I have this base of 2, it comes around here to the 3 and to my answer. So 2 to the third power is equal to this 3x minus 7 times an x minus 4. Now you solve. No more logarithms. All I have to do is just solve for x. So this is an 8. Foil that out, and you get 3x squared minus 12x minus 7x plus 28. So combine your like terms. And we get 3x squared minus 19x plus 28. Now this is a quadratic, so we're going to subtract 8 from both sides. And you get 3x squared minus a 19x plus 20 equals 0. Now let's factor that thing. Remember, when you factor, this is a 3x, a plus in the back and a minus up front, so I know they both have to be minuses. Now you're going to check your outside terms and your inside terms. So when you go through and you check your outside terms, I'm going to get what multiplies to give you 20. 4 times 5. So if you check your outside terms, you get a negative 15x for the outside. And then whenever you check your inside terms, you get a negative 4x. Negative 15 and negative 4 is that negative 19 that we want. My marker's not writing. There it is. Cool. Factored. So now I set each one of these equal to 0. It's a minus sign in there. Add 4, divide by 3, and x is a positive 4/3. Add 5, and x is a 5. Since neither one of those are negative, we don't have any issues. Both of them are our answers. So remember, if you just have a log on one side of your equation, you solve that by changing it to an exponential and then doing the work. Cool, let's do some more. And I super like this kind of problem, by the way, just as a side note, because it's previous information to the current lesson. Look at this, we're solving our quadratics. We did that way back at the beginning with our quadratics in chapter 1, and now we're bringing it back. Look at all this good practice. I love previous information into the current lesson. Ooh, look at this super awesome problem. Now I have a log just on the left side. We have logs not on the right. So I'm not getting like bases. I just have a log on the left, which means this plus sign tells me I need to put those together using those logarithmic properties. So I now have log of 3x plus 2 times x minus 1, because that plus sign in the middle tells me I get to multiply those. Now I have a single logarithm. Whoa, but what's happening here? If I don't have anything written down as a base, what is that automatically? If I just have a plain log, it's called a common log. What's my automatic base if nothing is written there? 10, good. So this is like base 10. Okay, now we can make that conversion. Take your base to the exponent and what it equals. So I have 10 to the first power now equals 3x plus 2 times an x minus 1. Cool. So let's do it. We got another quadratic on our hands. So 10 is now equal to 3x squared minus 3x plus 2x minus 2. So 10 is equal to a 3x squared minus x minus 2. So subtract that 10. 0 is now equal to a 3x squared minus x minus 12. Ooh, is this factorable? I don't think so. I don't think there's anything I can do to factor this out to make it work. All right, no problem. If we can't factor it, then what do we get the amazing opportunity to use? It should make you excited. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah, quadratic formula. How cool is that? That is amazing. So if I know I'm going to be doing quadratic formula here, I'm going to put a little line down the paper so that we can bring this problem up and get busy on it. So x is now equal to negative b, which this is our a, b, and c, right? So the opposite here of negative 1 is just 1, plus or minus the square root of b squared, so negative 1 squared, minus 4 times a times c, all over 2 times a. Cool, let's clean it up a little bit. 1 plus or minus the square root of 1 minus 144. Oops, sorry, that's a negative 12, right? Negative times a negative is a positive. Ooh, that was a close one. All over 6. So x is actually equal to 1 plus or minus the square root of 145 over 6. Now, this is whenever you gotta love that calculator. So you're going to type in both of them. X is equal to 1 plus or minus the square root of 145 over 6, and x is equal to 1 minus the square root of 145 over 6. So notice this first number is positive. Because the square root of 145 is way bigger than 1. So it's over 12, right? So this square root of 145 is a positive solution. But look at what happens here. If you were to plug in 1 minus the square root of 145, that's a super negative number. Remember, when you start with a logarithm, you cannot have a negative solution. So if you look at that negative solution, that one crosses off. Your only answer is 1 plus the square root of 145 equals, divided by 6. So your only solution to this problem is the positive one. Cool. All right. You guys are rocking this thing. Let's keep up the good work. Ooh, look at this big pile of awesomeness. Now don't get wigged out, because as soon as you see natural log, what do you think? E, good. And as soon as you see E, natural log. Well, look at that. They have it set up for you already. This natural log and E are touchy-touchy, so they cancel. This is really just the natural log of x minus the natural log of x minus 3 equals the natural log of 2. Not too shabby, right? I gave you a problem that looks super freaky, but in reality is not so bad. And look what's happening here. Natural logs on the left, natural logs on the right. So it's the same concept as getting those like bases on that equal sign. So put those things together with this minus sign. I know I'm going to be dividing. So I have the natural log of x divided by x minus 3 equals the natural log of 2. With those natural logs on both sides, those drop off. And I'm just left with x over x minus 3 equals 2. Now you just solve for that. Because it's a denominator, I multiply both sides by that x minus 3. They cancel on the left. X is now equal to 2x minus 6. I'm going to subtract 2x from both sides so I can collect those together. So negative x now equals a negative 6. But because both of those are negative, I'm going to divide by negative 1. And x is equal to a positive 6. As long as it's positive, we are good to go. Keep in mind, anytime you see E, think natural log. Anytime you see natural log, think E. They cancel each other out. It's not so bad. Great job, guys.